And now we get to two key definitions that are in the textbook that I'm going to view as applications of group actions. So the textbook defines them first and then shows how they arise, and then proves that they're subgroups, and then shows how you could get them from group actions. Instead, I will define them and then show how you could get them from group action. And then by the previous stuff we just studied, that tells you already have subgroups. So the first thing is called a centralizer. So here, A is now a subset of G. And so given any subset of G, the centralizer of A and G, it's good to write out how you read this out loud. Is by definition the set of group elements such that when you conjugate A by the group element, you get A. It's worth pointing out this conjugation business always looks kind of weird, but the other way to think about it is it's saying that you have commutativity, GA equals AG. So in other words, the centralizer is the set of group elements that commute with every element in your set A. As already mentioned, one of the cases that's important is called the center of the group. So the center of the group, under this interpretation that GA equals AG, it's the set of elements that commute with every other element in the group. So that's the definition of the center. Now we define the normalizer. We let P of G be the collection of all subsets of the group. Then it turns out G acts on this power set by conjugation. So G acts on A by GAG inverse. And how do you conjugate a set? Well, you conjugate every element of the set. And you can prove that this is a group action. I'll leave that as homework. And then for a subset of G, what is the stabilizer under this action? It's those group elements for which GAG inverse is equal to A. We define that to be the normalizer. So the normalizer of A and G is the set of group elements that when you conjugate, you get A back. It's worth pointing out that we often define things at this abstract level of sets, but in most applications, either A is going to be a single element or A is going to be a subgroup itself. And so if A were a subgroup, this would be the set of things that when you conjugate A by it, you get A back. In particular, if A is a normal subgroup of G, then you could see that the normalizer would be all of A, or all of G by definition, because that's what it means for a subgroup to be normal. And so in general, the normalizer is a subgroup that tells you how far away this, if A were a subgroup, it's telling you how far away your subgroup is from being a normal subgroup of G. And it's not too hard to see that we have this inclusion of subgroups. One just checks the definition. If G is in the centralizer, then what do we have? We have GA G inverse equals A for all A and A. But then that tells you that GA G inverse is capital A is definitely equal to capital A, which definitely tells you that G is in the normalizer. So the difference between these two statements is this is saying that conjugation fixes every element of A point-wise. So for each point, conjugation fixes the point, whereas here you're saying conjugation fixes the entire set. So in other words, conjugation could be permuting the set elements of the set among themselves, but you're staying in that neighborhood, so to speak. I guess abstract thought, if you think of A as a neighborhood of houses, being in the centralizer says that you've got some sort of permutation that keeps every house where it stood after the earthquake hit, whereas this one says that the houses permuted among themselves, but everyone still stayed in the neighborhood. And if you're not in the normalizer at all, then one of the houses just flew out of the neighborhood. Now let's take a look at some examples of centralizers and normalizers. First, let's assume we have an abelian group G, and let's let A be any subset. It's worth pointing out A should be non-empty. Well then, the centralizer is the set of all group elements that commute with every element in A. But, of course, since A is abelian, every group element commutes. So it's actually the entire group. Which means that's true about the normalizer too, because the centralizer is a subgroup of the normalizer. And so, we have this containment here. And we just showed that the last group is actually, the first group and the last group are the same, so everyone in the middle is also the same. So that ends that example. So let's pick something a little more interesting. Let's consider the dihedral group on 8 with generators R and S. R is for rotation, and S is reflection. And so we recall those are the usual relationships on the dihedral group. And so first let's consider what the center is of the dihedral group on 8. So these are going to be the group elements that commute with everything. Well, one thing worth noting is that a center of a group is certainly going to be contained in any centralizer. Just by the definition. Why? Because this is a much stronger condition. I mean, you can check whenever A is a subset of B, the centralizer of B is a subset of the centralizer of A. Why? Because this is a weaker condition, so it's easier to satisfy because of this universal quantifier. This is an intersection of sets, and here you're intersecting more sets, so it's a subset. So let's try to compute one of these centralizers, and the natural centralizer to compute first would be the centralizer of the rotation subgroup. It's the cyclic subgroup generated by rotations. So we're looking for everything that commutes with the rotations. Well, our relationship right here tells us that S is not going to commute with R. And so what are our remaining group elements? We have S, SR, SR squared, and SR cubed. So we've already ruled out S as an element. Similarly, we should probably be able to rule out these other ones. For instance, if I multiply SR by R, I get SR squared. On the other hand, if I multiply R times SR, I'm just going to get S by applying this identity. And so SR is also not in the centralizer. And similarly, if I multiply SR squared by R, what should happen? On one hand, I get SR cubed. On the other hand, I get SR. And so you can do the last one and as a sanity check, and you can see that these 4 elements of the group are not in the centralizer. So what is in the centralizer? Well, since A is in fact a subgroup and it's an abelian group, every element in A is going to be in the centralizer. In other words, every one of these rotations is going to commute with each other. And so we see at the very least E, R squared, and R cubed are all in the centralizer. And so we see that's all the centralizer is. Those are the only elements that commute. So we see that the centralizer in D8 of ER of the rotation subgroup is the rotation subgroup. And so now we see that the entire center of D8 is going to be a subgroup of the rotation group. So now we're just asking ourselves, which rotations commute with everything? Well, does R commute with everything? Well, no, because R doesn't commute with S, right? Because that's the relationship. So R is not in the center. Similarly, R cubed is not in the center. You might be tempted to think that the center's trivial, but there's one exception. If you multiply by R squared, what do you get? SR to the negative 2, but R to the negative 2 is R squared because we're working in D8, which means we're working with the symmetry group of the square. And so actually, R squared might work. One still has to check, of course, that R squared times any other power, SR to the I, but R to the negative 2 is the same as R to the 2. And so it does in fact commute. So R squared is in the center, and the identity is in the center. So we see that the center of D8 is in fact E and R squared. And this seems like it should be true for any even dihedral group, that E and R to the n over 2 should be in the center for the same calculation, because the negative half power is the same as the half power in the positive direction. Finally, since we're here, we might as well also compute the normalizer and see if it's different. So what is the normalizer of this subgroup? It's everything that when you conjugate, you get the whole subgroup. But we happen to know the cyclic subgroup is actually normal, so this should be all of D8. But we should check that anyways. What are the things we need to check left? We just need to check what happens when I multiply SR to the I times R to the J times SR to the I to the negative 1. Well, negative of the product is inverse product of the inverses in the reverse order. S negative 1 is just S. So we get R to the J times S inverse. Or I mean just S. Here I'm canceling out the R to the I and R to the negative I. And then that's just S squared times R to the negative J by bringing the S over. But S squared is the identity, so I just get R to the negative J, which is in fact in the subgroup generated by R. And so the check works. And in fact, this is how you prove that the rotation subgroup is normal in the dihedral group in general. It's this exact proof.